It's a little bit of a transition from the triangle congruence that we were talking about, and it goes into something that's known as coordinate geometry. Basically what you do is you take geometric shapes and you put them on a coordinate and algebra coordinate plane, and you look at the shapes and you try and determine things that you can, like using algebra, you try and determine if you have corners here or if the side lengths are the same, so maybe you can prove something's a square, like I said, something like that. So if you can prove those angles are corners and the side lengths are the same, then you can prove something's a square. This video is going to jump around a lot from like coordinate planes, etc. So I'm going to start with 784. I've jotted down some notes because I'm going to have to go to a coordinate plane and answer this, but it says review some of the algebra tools you already have. Consider two line segments A, B, and C, D. So we're given these points, and it tells us to draw these two segments on a coordinate grid and then calculate the length of each segment. From there, we want the equation of A, B, and C, D. In the equation, y equals mx plus b. It wants to know the relationship. Are they parallel, perpendicular, neither, and justify. And then we need to be able to figure out the intersection of A, B, and C, D. So in order to do that, like I said, I'm going to have to go to a coordinate plane. And the normal coordinate plane I use isn't big enough, so I had to make a bigger one here. So on this, we're given the coordinates, and the first one was 0, 8, and this was point A. The second one was going to be 9, 2, and this was going to be point B. So we want a straight line between A and B. From there, we were given point C, which was 1, 3, and we were given point D, which is 9, 15. And again, we'll draw a straight line from those 2 points. All right, so that was what A asked us to do, and we should get the length of these. Now, when we get the length of these, I have no idea. Like, it's easy to tell what the length of something is when it's going horizontally or vertically. But when it's going diagonally, it's not so easy. But what if we turn it into a right triangle and use the Pythagorean theorem? So that's going to be our strategy here. We're gonna use this as a right triangle. So we're going to go over here, like I said, and we're going to turn this thing into a right triangle. So it goes up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it goes over 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have a 12 by 8 triangle. So I should be able to say 12 squared plus 8 squared equals the length of CD squared, right? So I'll go to my calculator and I will do that. 12 squared is, of course, 144. I don't even know why I'm figuring it out. And I'll add to that 8 squared, which is 64. So we get 208. Well, this distance is going to be the square root of 208, which ends up being 14.4. So I know the distance of this one is going to be about 14.4. And I hope that makes sense because I was able to make a right triangle. Well, I'll do the same thing here. I'll make a right triangle here. So this one is 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, 7, 8, 9. Couldn't be too easy to be a 6 by 8. That would have been so much easier. But long story short, we know 6 squared plus 9 squared is going to equal AB squared. So again, I'll use my calculator. I know that 6 squared is 36, plus 81 is 9 squared. So the square root of 117 will equal AB. So I'll take the square root of 117 and I get 10.8. So I know that this distance is about 10.8. And again, I did that using a strategy you're going to want to know for the rest of this chapter, turning these things into triangles and using the Pythagorean theorem. So that will be something that you're expected to know how to do on the test. So make sure you don't forget that strategy. You can see it's having a little bit of trouble erasing the straight lines, but it looks something like this. Okay, so that was A, asking us to do that. B wants us to get the equation of A, B, and C, D. So again, I have this point 1, 3, and I have this point 9, 15. So what I can do is figure out the slope, which the slope was up 12 and over 8. So my slope here was 12 over 8, which is 3 over 2, right? If I simplify that. And then I can just use this as my x and my y. So I'll sub it into the equation y equals mx plus b. I think this goes back to like chapter 2 where we did this, right? So the y is 3, the m is 3/2, the x is 1 plus b. So 3 equals 1.5 plus b. Subtract that, I get 1.5 equals b. So the equation of this line right here is going to be y equals, I guess we could say 1.5x plus 1.5. And that makes sense. If you follow this down, you can see the y-intercept is about 1.5, and then I just go up 1.5 and over 1, and up 1.5 and over 1, and up 1.5 and over 1. And you can see that's a pretty good equation for that one right there. I will do the same thing for this equation, and this is 0.08, so that's nice. We already have the y-intercept is 8, and then we know this is 0.92. So really all I need my slope, since I already have the y-intercept. So I'm going to go down, it was down 6 and over 9, right? My slope was -6/9, which is the same as -2/3, and again I have my y-intercept as 8. So this equation would be y equals -2/3 x plus 8. And you can see I'm at 8. I go down 2 over 3, down 2 over 3, down 2 over 3. So that equation makes sense as well. So if we look at C, it says, what's the relationship here? Are these parallel or perpendicular or neither? So we're going to kind of look here. If they're parallel, they have to have the same slope, and clearly these don't. If they are, don't forget, 1.5 is 3/2. So if they're perpendicular, the slopes have to be negative reciprocals. So are these, again, 1.5 is 3/2. Is this slope a negative reciprocal? It is. So we can confidently say that this is a right angle. We know this is a right angle because we have perpendicular slopes, because they are negative reciprocals. So we begin to get into the usefulness of coordinate geometry, right? We have these geometric shapes, but we're using algebra to prove that that's a 90-degree angle. We're using algebra to prove this length is 10.8 because we have the Pythagorean theorem. We have the same thing for this 14.4. And then finally, we should get the intersection. Well, it definitely looks like the intersection is 3, 6. I think we can all agree that's what it looks like, but it's asking us to prove it algebraically. So I know that this equals y and this equals y, and I'm going to convert this over to 3/2 because I'm going to go fractions the whole way here. So I know that 3/2 x plus 1.5 is equal to -2/3 x plus 8. Well, what I'll do here, again, I said I was going to go fractions the whole way, and then I didn't, so this is 3/2. I'm going to use fraction busting. So I want a number that 2 and 3 both go into. They both go into 6. So I'm going to multiply everything here by 6 to break these fractions. This is going to be 9x. This is going to be plus 9. This is going to be, don't forget the negative, right? -4x. And this is going to be 48. I'll subtract 9. I'll add 4x. And I get 13x is equal to 39. I'll divide both sides by 3. So x is indeed 3, just like we suspected. And if I plug x into one of these equations, and I definitely think I want to plug it into this one because it'll cancel out, right? So here's what I mean by that. If I plug x into this equation, 3, and for x in this equation, I get y equals -2/3 times 3. There's going to be some cross canceling plus 8. So that cancels. I get y equals -2 plus 8, which is 6, which again is what we suspected, 3, 6. And then finally, I'll check it in this equation. What if we plug in 8 here, right? I'm sorry, 6 here for the y. So 6 equals 3/2 times 3 plus 3/2, or 1.5 3/2. So I'm going to get 6 equals 9/2, which is 4.5 plus 3/2, which is 1.5, which does check. So you can see I use algebra to solve that. So a lot of work here. Again, that was the entire problem, A, B, C, D. I just jotted down those notes and went and wrote those down. So next, we will reopen this, and we will do 785. 785 says open this resource page, and then go ahead and go through the properties of it. And I don't know if I'm going to go through the whole thing because I'm not sure how long this will take, but I do want you guys to see kind of how this works. So if I go back through chapter 7, 721 resource page, we get a sheet that looks like this. And essentially what it says special properties. I don't want you to write this out. I think what you should do is use these ticks. I know that this is the same as this is the same as this. Again, if it's a regular hexagon. Also, I know that the angles have to be the same. A regular shape, pentagon, hexagon, whatever, it doesn't matter. It just means that the angles on the sides are the same. But not only that, the opposite sides are also parallel. So this is going to look messy quickly. And I'll kind of leave it at that, but you can see that I would have to use a different amount of, like, I can use one tick for all these because they all have the same length, but I can't use one caret for each because, like, this line's not parallel to this one. So these have 2 carets, these have 1 caret, these have 3 carets. So kind of a mess. A kite, we know that this is the same as this, and this is the same as this. And actually, these angles are the same as well, but this is not the same as this. A rectangle, we have some squares, right? And we know that the opposite sides are not only congruent, but they're also parallel. So you can see there's a lot of things. If you want to write it in English, you can, but we need to get good with these symbols. So I think that's a good idea. A scalene triangle is a pretty simple one. It just means everything is different. Here, a trapezoid, the opposite sides are parallel. That's all a trapezoid means. Equilateral triangle, all the angles are the same, and all the sides are the same. A square, all the sides are the same. They're all 90-degree angles, but don't forget the opposite sides are also parallel, which gets to be kind of a pain to put this stuff in. An isosceles right triangle. Isosceles right triangle means that, don't forget, on an isosceles triangle, not only are the sides the same, but the opposite angles are also the same. And if it's a right triangle, we have to put that corner in. Got some more shapes. Circle, I don't know what we'd really say about a circle. I mean, I guess the radius is the same everywhere along, but whatever. A rhombus is like a squished square. All the sides are the same. The opposite sides are parallel, and the opposite angles are the same. However, they're not the same as each other. So like these angles are the same, but they're not the same as these angles, but these angles are the same. Quadrilateral just means it's 4 sides. Nothing special here. So I guess if it's not special, we can just say all the sides are different, although I don't know that we really need to. Just a quadrilateral just means it's 4 sides. Isosceles triangle, again, we already talked about that a little bit. Don't forget that the angles, the base angles are also the same along with the sides. A scalene right triangle would just mean that it has a right angle and that all the sides are different. An isosceles trapezoid means not only are the opposite sides parallel, but that the legs are the same, meaning that the angles have to be the same as well. Parallelogram is like a squished rectangle, so not only are the opposite sides parallel, but they're also congruent. And then the opposite angles will also be the same. But again, these are the same as each other, and these are the same as each other. And again, I know these look like a mess, so hopefully you're kind of paying attention as I go through it. And then the final one, a regular pentagon, again, it just means all the angles are the same and all the sides are the same. However, there are no parallel sides, so it's not as messy as a regular hexagon. So that's just a little bit about some of the shapes that we should be familiar with going through here. Finally, we have um, 786. Again, we're going to end up having to graph this. Am I special? we have to plot these 4 points, and then we figure out the perimeter. We figure out if it's a quadrilateral or not. We figure out, I'm sorry, if it's a trapezoid or not, I should say. We figure out if it is it any other kind of shape, and then if it has any special properties. So what we're going to have to do here is go to, again, I've taken some notes on this. So we will go here and we will go with the regular coordinate plane. And I will jot this down. We had S at 0, 0. We had H at 0, 5. We had A at 4, 8. And we had Y at 7, 4. I'll go to the straight line tool and kind of fill in the shape. So the first thing we had to do was get the perimeter, which is kind of a pain, but definitely doable. So the perimeter here, obviously this is 1, 2, 3, 4, 5. It's vertical, so it's easy to tell the distance here. This one we're going to have to make our right triangle, right? 3 squared plus 4 squared equals 5 squared. So that was pretty simple. Here, 3 squared, I'm sorry, 1, 2, 3, 4 squared plus 3 squared, again, equals 5 squared. So that really let us off the hook on the first two. But the last one, not so much. We have over 7. Yeah, that looked really bad. Sorry. So down 4 and over 7. So we're going to get 4 squared plus 7 squared is going to equal to ys squared. Again, we'll grab our calculator here. Obviously 4 squared is 16, and obviously 7 squared is 49. So we want the square root of 65. So obviously the square root of 64 is 8, so it's barely more than 8. So we get about 8.06. So a couple things I'll say here. I actually prefer that you say the square root of 65, but it doesn't really matter, I guess, at this point. So we used our slope triangles, our Pythagorean theorem, to figure out these lengths. So the perimeter of this shape is either going to be about 5, 10, 15, 23.06, or we could say it is equal to 15 plus the square root of 65. Either one of these is acceptable. And again, if you don't believe me, look what happens when we go here into the calculator and we put 15 plus the square root of 65. What the heck? I don't understand what just happened there. Anyways, if we get 15 plus the square root of 65, we get about 23.06. So either of these is acceptable. This is a precise answer, so we can use equal. This is an approximate answer, so we use the about symbol. Anyways, that's the perimeter. Now we want to know if this is a trapezoid. Is there any parallel sides here? Well, what we'd have to do is figure out the slopes. Obviously, the slope here is undefined. It's straight up and down, and the slope here is not undefined, so these can't be parallel. But these ones possibly could be. So let's see if they have the same slope. Up 1, 2, 3 over 1, 2, 3, 4. So this has a slope of 3/4. This has a slope of 1, 2, 3, 4, and over 1, 2, 3, 4, 5, 6, 7. And you can see that's not the same slope, right? So these are not parallel. So I would say no, this is not a trapezoid. So the question is, does it have any other sort of fabulous thing? Is there? No, it's just a quadrilateral, right? This isn't any kind of a special shape that we've learned. So C will say no, there's real no name. It's just a quadrilateral. And then finally, is there anything special? Well, we already determined that 3 sides are the same length, so that's something. Another thing is, look, this slope is up 3/4, and this slope is down 1, 2, 3, 4, and over 3. So we have negative reciprocals. So this is a corner. This is a 90-degree angle. But again, nothing that we can really say is fantastic. Just some special properties. 3 sides are 5. So 3 sides are congruent, but this one isn't. And then finally, we do have a corner. We have a 90-degree angle. This one, not so much, though. It's close to a 90-degree angle, but we've already determined that the slope isn't a negative reciprocal. So that is it for this lesson.